This lesson will explore some very foreign and scary sounding terms, including degeneracy, quantum, Coulomb barrier, helium flash, degenerate electron pressure, and helium fusion. I hope I didn't scare you away already. Those terms sound pretty bad, and they're actually quite complex. However, I will simplify them for you in a logical manner, so you can go and brag to your friends about your newfound knowledge after you nail everything down. All of these terms can be used outside the scope of this lesson, but for right now, we'll focus in on how they relate to helium fusion in red giants, stars that have run out of hydrogen to produce energy. Before we can explore how red giants generate energy, we have to take a small step back and explore the properties of gases like those found on Earth. In most cases, the way gases behave on Earth correlate well with the way they behave inside of a star. How do these gases behave? Really quickly put, the pressure exerted by a gas is directly proportional to the density and the temperature of a gas. When you compress a gas, it becomes denser and its temperature increases. When the temperature increases, the pressure increases. Inside of a main sequence star, an adult star, one that fuses hydrogen to produce helium in its core in order to generate energy, there is a sort of safety valve system that uses this principle. A normal adult star doesn't expand like crazy, nor does it collapse, because of an equilibrium maintained between the inward force of gravity trying to contract the star and the expansive outward force of gas pressure fighting against gravity. The stalemate between such forces maintains the star's shape and temperature. It's like a spring, where you can press downward on the spring, but the spring will push up against you to try and resist the compressive forces. If, for example, the rate of nuclear reactions in the star's core were to decrease, the core would cool down and it would contract due to the now overbearing inward forces. But such compression will actually increase the temperature inside the core as per the gas rules I outlined before. Increasing temperatures speed up the rate of thermonuclear reactions, and the core would expand back to a normal size. However, if the thermonuclear reactions were to increase by way too much, the core would expand as a result, cool as it expands, and thus eventually contract back down to normal. But this isn't how things work in red giants that have masses that are between approximately 0.4 solar masses and about 2 to 3 solar masses. Red giants with more than about 2 to 3 solar masses undergo a gradual onset of helium fusion, as opposed to the former ones, which undergo an explosive helium flash. A main sequence star burns hydrogen and produces helium during its thermonuclear reactions in order to generate energy. Once the finite amount of hydrogen in the core is depleted, it logically becomes a helium core. But the helium doesn't immediately fuse to produce energy thereafter. That's because the core is initially not hot enough for this. Helium requires much larger temperatures to undergo thermonuclear reactions, which produce carbon from helium. This is because helium nuclei have positive charges that are twice that of hydrogen nuclei. It's sort of like the helium nuclei are much more powerful opposing magnets than hydrogen nuclei. This means that you will need much higher speeds to overcome the Coulomb barrier, which refers to the electrostatic repulsion between two or more bodies of similar charge that must be overcome for nuclear fusion to begin. The only way to get these higher speeds in the core is to increase the temperature of the core. Thankfully, as a giant star burns through its remaining hydrogen, gravity will compress the helium core into a very small size. As you know, this will increase the temperature more and more. And normally, this would also increase the outward pressure of the gas, causing the core to expand and cool thereafter. But Something different happens under such extreme pressures, densities, and temperatures as those generated by red giants. Quantum mechanics comes into play. Under such large inward pressures and temperatures, the atoms lose their electrons and are completely ionized. This means the core is made of atomic nuclei and free electrons. But the free electrons become so tightly packed in the core that they cannot compress any further. They produce a very powerful pressure that will resist any additional core contraction. This process is called degeneracy, and the electrons I spoke of are termed degenerate. This means the core is held up by degenerate electron pressure, pressure that does not depend on temperature. This notion is completely the opposite of normal gas laws I referred to before. As a result, when the temperature in the core reaches the level necessary for the triple alpha process to begin, then energy can be released. The triple alpha process is when 3 helium atoms form carbon during a nuclear reaction. The helium heats up even more, and this process begins to occur even faster. But the increasing heat due to degenerate electrons does not change the pressure. This means the core doesn't expand and cool, and because of this, the temperature rises faster and faster, and helium fuses at ever-increasing rates in a sudden and explosive manner that's called the helium flash. This helium flash generates more energy per second than an entire galaxy. The pressure exerted by a gas is directly proportional to the density and the temperature of a gas. But when the helium core of a red giant begins to contract, this isn't really the case. That's because free electrons under extreme pressures and temperature can't contract any further, and while the temperature rises in the core, the pressure does not. This process is called degeneracy, and the electrons are termed degenerate. This means the helium core is held up by degenerate electron pressure, pressure that does not depend on temperature. High temperatures generated in the core help helium nuclei overcome the Coulomb barrier, which refers to the electrostatic repulsion between 2 or more bodies of similar charge that must be overcome for nuclear fusion to begin. The helium nuclei crash into one another and the triple alpha process begins. This is when 3 helium atoms form carbon during a nuclear reaction.